Hi everyone, people in the space and people online. Let me before I share my screen. I could show you something, some piece of hardware. So, some people might be aware of the mechanical keyboard. Sort of like, I guess it's kind of a niche thing. Although when you're in it, there's lots of stuff going on, so it doesn't feel niche. But lots of people like to build their own keyboards. And there are many different kinds of keyboards that you can build. You can build your own. You can go on GitHub and get people's schematics and print the PCB and then build it that way. Or you can buy kits to assemble, or you can buy pre-assembled kits, or you can back a Kickstarter that makes it. There's this very vast array of mechanical keyboards out there. I used to type on a happy hacking keyboard for like, I don't know, 10 years plus or something, which I really liked. It had capacitive keys, so there wasn't actually a switch that contacted. It was measuring the capacitance of the depth of the key press. It was a good keyboard, but my wrist started to, well, play up and get painful in my fingers. And so I investigated into split keyboards, which is when the left and the right half of the keyboard are split into separate physical keyboards. And you can place them as far apart as you'd like. And so my current keyboard is this one here. So these are the two halves. Can everyone see this? I'm trying to make it fit in the thing.
It looks like a crazy person's laid out the keys though.
Yeah, so there's half here. So it's actually Dvorak layout as well. It gets reflected in the thing. But also, not only is it, this is actually the right way up. It's in the shape of your hand. Not only is it split in half, but it's also, the columns are linear or orthogonal. So instead of being staggered like on a normal keyboard, it looks like this. And then you have a lot of different keys for your thumbs, like a thumb cluster, so that you can do more with your thumbs instead of just hitting space. And so you have two separate halves, and they're joined together, and one of them is plugged in via USB to the computer. And then it works like, it doesn't work like a normal keyboard. It works like a keyboard, but it's quite different to a standing keyboard, because you probably noticed that there are no numbers or symbols. There's just the basic letters, and a few extra keys like enter. So the numbers all exist on a layer. So when you hold down, for example, this key, no, actually it's this one. No, this one. Then you get a numpad on your hand. So you can actually configure it however you like to do really whatever you want. And configuring a keyboard, you can spend a lot of time doing that to tune it to your particular workflow and the way I use Vim, so the sorts of keys I press are a bit different maybe from if you used Emacs, for example. So I'll just start sharing my screen now so I can show you a few more things. Share entire now. Yes. Can you see this? Yep. So this is where I bought this keyboard from as a kit, splitkb.com. It's actually in the Netherlands. Highly recommend ordering from here if you are interested. They have a lot of different keyboards, and you can choose the kind of keys you like, high profile or low profile for the switches, and then the keys as well you can change. And there's a whole bunch of different options they have for keyboards, like really small ones that have very few keys. And you can also get larger ones that have a lot more. So I got mine from here and I built it. It took quite a while to build, actually, to solder everything. There's quite a lot of soldering to do, but it's fun and it's rewarding. And then once you have a keyboard, you put firmware on it. And there's sort of two main competing firmware that you can download. One is QMK, Quantum Mechanical Keyboard, is what it stands for. So this is using Chibi OS as sort of the main operating system. And then on top of that, they've implemented keyboard functionality using USB HAD. And you can customize it a lot. Although you have to do it in C, it's all written in C. The other competing one is called ZMK, which is a Zephyr mechanical keyboard. So this is based on Zephyr operating system and or real-time operating system, which you may have heard of. And then this has all features for keyboards. The reason you would use this one is because it got support for Bluetooth for a wireless keyboard. QMK does not support Bluetooth. So that's cool. Yeah, you can get both halves basically of the keyboard have Bluetooth and a battery, and they're just completely wireless. You have like a peripheral keyboard that talks to the central, and then the central is then also a peripheral to your PC. That's how they work. And then there is actually another, there's a CircuitPython version called KMK, Clackety Keyboards, which is, as far as I can tell, it's not that popular, but does have support for some keyboards using CircuitPython, obviously MicroPython based. But the point of all this that I'm talking now is that I used MicroPython to re-implement the firmware on this keyboard that I showed you. So originally it came with QMK firmware, but I rewrote it because it was quite a lot of fun, and it means I can customize it even more. So the code I have here, I finally got this working not only a few days ago after mucking around a lot with it. So the actual keyboard itself has two RP2040 controllers, one on each side. So you've got the left-hand one and the right-hand one. Otherwise, it's actually very simple. There are not really any resistors. The keys have diodes in a matrix. And then the microcontroller just scans the matrix to see which keys are pressed. And then you can send that out over USB. So the code that I've written has some different components here. So maybe we can start with the matrix reading code. So basically, you just have a bunch of pins for the columns and a bunch for the rows. And you can imagine that makes a matrix of keys. I do have the schematics. Maybe that's useful. Yeah, here we go. So this is the schematics for the keyboard. Pretty simple. You have this matrix here. The switch matrix has a bunch of columns and rows and diodes and switches, and that's about it. The rest of this is a NeoPixel per key, which I didn't actually install because I didn't really want to have colors per key, but I did put underglow on, which is 6 NeoPixels on the bottom to make the bottom of the keyboard glow. You can add encoders, but I didn't do that. So really all it is just a bunch of diodes and switches in a matrix. And then a microcontroller attached to each left and right half, which comes as like a little board that you plug in, but it's really just an RP2040 with like flash and an LED. So it is a very simple electronic design, but mechanically it's quite complicated the way the switches all fit together, and there's like multi-layer. You've got 2 layers of PCB, or actually, yeah, 2 layers of PCB and some perspex. But the matrix reading code here, there's just a function down the bottom which does the actual scanning. So you go through every row and you set the row pin to be low. And then when that row pin is low, you go through every column and see if that column pin is pulled high or not. Sorry, so pulled low by the row. And if it is, then that key has been pressed. So in this way, you can distinguish between all the keys. So each half on my keyboard has 25 keys, I think, 27 keys. And you can distinguish each one individually using this code and the way the circuit is made. So this is sort of the core function which does the detecting of key presses. And it just returns an integer, which is a bitmap of which keys are pressed. So 27 keys means this has like 27 bits, which fits in a a small integer. So that's good. And I made this function a bit faster by wrapping it in MicroPython native, and it takes about 200 or 250 to 250 microseconds, to run, to scan the entire keypad. And remember, the left and the right act totally independently. They have independent microcontrollers running. The rest of this code is just a map for which key in the matrix you press corresponds to the key number, just so that the keys are numbered 1, 2, 3, 4, 5, 6 from top to bottom. So with this, it's pretty simple. Once you have a key press, you can then send it over USB to say this key is pressed. And I'm just using the built-in MicroPython lib keyboard code, and I'll show you that in a second. But first of all, we need to, because we've got two halves of the keyboard, they have to talk to each other. They're not independently plugged into the PC. The right half is plugged into the left half, and the left half is plugged in via USB. So the two halves have to talk to each other, and the way they're connected is through like a single wire protocol for talking, for communication. And I needed to implement UART using the PIO because it didn't have a hardware UART on the pin that was connected through. So there's a simple PIO-based UART class that I've taken bits and pieces of code from the examples. So there's an example code we have already in the repository for in MicroPython for making a UART RX and TX using PIO, which is this code here. So that's part of this this small bit of the module. You can basically read and write bytes, send bytes between the two halves.
Perhaps for those that don't know what PIO is, come chat with us later. It's a pretty cool feature of the Raspberry Pi RP2040.
Yeah, so you can program GPIO with a little state machine to do whatever you want. So the receiver is very simple, and the transmitter is also extremely simple. But you really need, I tried doing it in software first without PIO just for sort of fun, and it was really hard to get it accurate timing. But the PIO is very simple to get accurate timing. And the baud rate I'm running it at, I think, is 100 kilobaud. So yeah, 100,000 baud. So that's not too slow, but it's not fast either. This file here is just defining the pins and the layout of the microcontroller and how it's connected up. Which pins on the microcontroller are the columns and the rows for the left half and the right half. They're just different. And then we have like a NeoPixel class to control the NeoPixel. There's a power LED, and this rest of it is just defining the pins. So this file here you could change if you had a different microcontroller. Just change your pin out. So just to show you, so we've been through the the UART code to create a UART code to communicate, the matrix code to scan the keys. The baud file just defines the pins and the LEDs. Maybe the next thing I could show you is the layout, which is the interesting one. So this is the way you configure the key layout on your keyboard. So this is the bit that's really customizable. So this is sort of supposed to be in kind of the way the keyboard actually looks. There's the left half and the right half. And there's 3 different layers here. So on the base layer, which is what it's called, when you don't press any keys, you get your basic A to Z. Here it's in a Dvorak layout, but you could change that to whatever you like. People like to use Coleman these days. But I learned Dvorak a long time ago before Coleman existed. So that's what I use. And the thumb keys, which is this bottom row here, So I have like a shift and a space and the like the Windows key. And then these two ones here change layers to layer 1 and layer 2. So if I hold this key, I get the next layer. And if I hold the other key, then I get keys on the third layer. You can consider this first layer as layer 0. So the definition of layer 1 is here, and then layer 2 is at the bottom. So layer 1 has all the numbers in a numpad layout on the left hand, and all of the symbols on the right hand in the same sort of numpad layout mirrored. And you get, well, a few other things. You notice I've actually have backspace on the layer, so you have to go to a layer to delete things. My philosophy there is that you shouldn't be making mistakes, so you shouldn't need to backspace often, but I often do. So, and the third layer currently is just used for motion up, down, left, right, page up, page down. And so there's obviously a lot of room left to add other things, like you could add function keys and mouse. Some people put a mouse on a layer so you can actually pretend to have a mouse as well. But this is the thing you would customize and tweak to make your typing experience fun. So the keys, you see, all these symbols here, like A and quote and everything, are defined in the keys file, which is just a convenience file for defining keys and defining shifted versions of keys. And it uses a lot of key codes from our MicroPython lib driver, which is available online. Most of those basic ones you saw, I've just defined a few extra here and some shortcuts. So that's that part of the code. So I think that's all the sort of the auxiliary stuff. All that's left is really the main keyboard driver, and then the boot code as well. So the boot code's interesting because it's a USB keyboard. The REPL kind of disappears when you turn it on. So I've made 3 different modes when you turn the keyboard on. If you're holding down a certain key, it actually goes into the bootloader, so you can change the firmware. So when it boots up, it scans the matrix, and then if you're holding down the bootloader key, it goes straight to the bootloader. If you're holding down the REPL key, then it just drops straight into the REPL and doesn't actually start the keyboard. So that way you can sort of, use MP remote and change things. Otherwise, if you're not holding down those keys, it will actually start the keyboard. But you can actually go into debug mode, which is when it will start with a REPL and a keyboard at the same time. And so if you plug both halves in to your computer and start them both in debug mode, they'll both be like MicroPython REPLs as well as a keyboard. So you can get a REPL on both halves of your keyboard at the same time as using the keyboard. So that's pretty funky, but good for debugging. So this boot code here just detects, the code is here so that it can choose how the USB is set up. And once that's done, it goes into main, and then main simply just, if we're trying to boot the keyboard, it'll just run the keyboard code. It's best to put your application logic in main rather than the boot.py. So we've been through all of the different parts here except the main keyboard code, which is the most complicated of the software. Now it uses async IO, and not sure where to start here, but at the bottom, the main run code, it just detects if it's running the left or the right half, which you can tell by a pin being pulled high or low, then it either runs the left or the right main function. And the left or the right main function is just waits forever an async IO task that will never finish. It's just the main async IO task. So there's an async IO task running on the left and one on the right hand keyboard. And then I also made a little RGB task to fade an LED every time you press a key. But there's a lot more funky stuff you could do with animations, and some people put displays on their keyboard and everything. There's lots you can do. So probably the simplest thing is the right half of the keyboard, which is here. and the right half of the keyboard, all it does is just continually scans the matrix in a while true loop. And if any of the keys have changed, so it compares the current scan with the previous scan, and if any of the keys have changed, it just writes that data out over that PIO UART that we saw to the left-hand side of the keyboard to say this key was pressed or this key was released. So there's a bit that indicates whether it's pressed or released, the high bit of the data, and the low 7 bits is the key number. So it's just the right-hand side, all it's doing is just scanning the matrix and saying key 1 was pressed, key 1 was released, key 2 was pressed, key 2 was released. That's all it does. It's very, very simple. And there's a delay of 1 millisecond for each iteration. And I haven't noticed any problem with latency. It's very, very quick. So really all of the work is then in the left-hand side of the keyboard. So the left-hand side, which is this large function here. So this is the code that sets up the USB, which is very simple because it's all in MicroPython lib. You just construct this keyboard class and then initialize USB using the keyboard, and also optionally have the REPL as well, depending on how you boot it up. And once you've done that, you can then call keyboard.send keys, and you give it a list of keys that you pressed, and that's it. So the loop, the main logic below in this loop is just to work out which keys to send. And this is sort of the complicated stuff. I won't go through all this because it's a bit tricky, but I'll put this stuff eventually on GitHub and you can have a look. Basically, it just scans the matrix to see if any new keys have been pressed or released, just like the right half would. And then also see if there's any data from the right half for any of the keys it had pressed. And so it just reads data from that UART. So this bit of the code is collecting any keys that have been pressed or released. And then there's some complicated logic here to map those key presses, like key 1 was pressed, to key 1 equals Y. Or if you're on layer 2 and key 1 is pressed, then it's the number 0, for example. So this is using that layout that we saw before, this code here, to map from key number to the actual letter or number or whatever you press, the up arrow key or enter or backspace. It's also got support for sticky keys. So sticky keys is when, for example, shift is sticky. So I can press shift once and let go, and then the next letter I press is going to be shifted. So I don't actually have to hold down shift. And that's actually quicker typing, I find, than holding down shift and pressing A. To get capital A, I just press shift and then press A. I feel I can type faster that way. So once it's found all the keys, it then sends them to the host back up over USB, but only if something's changed, not to keep sending things unnecessarily. I have a slightly modified version of send keys, which does some special shifting if necessary. And after that, yeah, it updates the sticky modifier. So if you press shift and then you pressed A, it's got a release shift as well after you actually press something. You don't want shift to be held down the whole time, for example. So yeah, writing this code in async.io I think was really good. It's a lot of fun. It's very simple. There's not actually that much logic to it, and there's a lot of room for customization of, you can have it so that if you press 2 keys at once, it does something else, or yeah, some people, yeah, there's a lot of different things you can do. If you hold a key, it can have a different action to if you tap it. For example, if you tap A, it's an A, or if you hold A, it's shift, for example. And this way, people can get away with keyboards that have very few keys on them. There's a little bit more sort of boilerplate code here, which was converting this layout to a more usable data structure. The RGB task, which fades an LED every time I press a key, just for fun. And then the keyboard class, which is just sending these custom keys, just to make special shifted keys if necessary. So that's all in this file. So I think that's pretty much it. Yes. So you can see, let's see, how many lines of code is there? 500 lines of code to implement a USB keyboard. That doesn't include the low-level USB driver stuff, but all the custom code that I've shown here, 500 lines to implement all that. And it was a lot of fun to make, and I still got a lot of customization left to do, trying out different key maps and things. You can spend a lot of time with mechanical keyboards. They're a lot of fun. So just to go back, if you want to learn more, I suggest looking at this splitkb.com site. There's a lot of interesting kits there, and they have a big community around it. You can also look at this QMK. There's a lot of keyboards there and layouts. You can have a look. People, if you go to like the layouts, there's usually a diagram for each one. Default. You can see there's hundreds and hundreds and hundreds of keyboards here, and they have the layouts and diagrams. So quite interesting. I haven't looked much into this CircuitPython Clackety keyboard, but I wanted to do it myself to see if it was possible, and also to see the things we can improve in MicroPython to build these sorts of projects. I didn't really find anything that was lacking, except maybe soft reset cores on RP2 port I had to add. So that's it. Thanks for listening. If you have any questions, I can show you the keyboard again so you have an idea what it looks like. It's a bit crazy.
That's cool.
That's the right half.
That's really cool.
What's the what was the name of this layer?
What do you mean, Dvorak?
Oh, sorry, the actual keyboard.
The keyboard is called a Kyria version 3.
Cool.
So you can see I've built the low profile version. So these are low profile switches. You can see the different layers in there. There's perspex, 2 PCBs, and then switches and keys on top. The Kyria Rev 3. I find that I don't actually use these 2 keys here at all. They you can see the and I also don't use these 2 here. I only use 3 of these thumb ones.
Yeah, nice. I'm gonna have to give it a go.
Yeah, it's a pretty big, deep rabbit hole to go down if you start.
I might have to. I've got a split keyboard, but I might need to make another one so I can experiment with this on it, because it might cause problems if I break the one that I use, I guess. But
which keyboard do you have?
Oh, I've got a an Ergodox.
Ergodox. Yep. I find it definitely the biggest benefit I find is it being split is you can have your arms at shoulder width, and that helps a lot with the nice. You've got something. Oh
yeah.
What is that? Is that a sweep?
Ferris sweep. With nice nanos.
Yeah, they're the Bluetooth ones.
Yeah.
How do you find that sweep? Is it enough keys?
I love it.
You love it,
yeah. Like you said, I think I've got one less thumb key than you actually use, so it's pretty good.
I've got an extra column compared to you. I got 6 columns.
Yeah, but I'm happy I can get the whole alpha layer on here.
Yeah, and
just symbols are on another layer, and so it's pretty good.
Yeah, well, I don't have to convince you then. I want to get a corn next, which is a little bit smaller than mine, but still bigger than the sweep.
Oh, yeah.
Where did you get yours from?
I just built it myself. Got the PC. You can just get the got the KiCad files, made a few changes, and just got them from JLPCB. Pretty cool, pretty quick and easy.
But sorry, to answer your question, the next board I wanted to get would have Bluetooth, would be nice nano based. And so that would really push me and motivate me to get that working with MicroPython. I think Andrew Leach's work to get Bluetooth working with Nimble on the NRF port will be needed for that. Yeah. So
thanks, Andrew. In
that is
advance.
on
That did just get rebased recently, I think. So it should be pretty. It mostly works.
Cool. So yeah, that
Excellent.
would be great to get that working.